Good morning, good evening, and good night again. This is Gang Chen from MIT. Welcome to MIT Innotherm Colloquia number 6. And today's colloquium is on battery thermal management and safety. And I'm very excited to have this excellent list of panelists. I'll leave this to moderator Christina Amon to introduce. So let me introduce Christina, our moderator today. Christina is a friend, and she's currently professor, alumni, distinguished professor in bioengineering from the University of Toronto. And she served as Dean of School of Applied Science Engineering of University of Toronto, and director of the Institute for Complex Engineering Systems at the Colloquia. She is a member of Canadian Academy of Engineering, Hispanic Engineering Academy of National Academy of Engineering, and the Royal Academy of Spain. And actually, my blocked. And her research in the nanoscale thermal transport, thermal fluids, and engineering systems. So with that, let me welcome Christina and turn the podium to Christina. Thank you.
Let me now share the screen. Can you see it?
Yes.
Yes. All right. So thank you, Gan, for introducing today's Innotherm Colloquia on thermal management of and safety for batteries, a topic that it is of great relevance, more so with the increasing adoption of electrical vehicles. And thank you to our colleagues at MIT, Gan Chen, Asegun Henry, John Linhart, and Evelyn Wang, for envisioning this colloquia on thermal innovations, which brings together researchers from thermal fluid sciences and beyond to share our knowledge in emerging and relevant topics within thermofluids. Again, welcome everyone, and I appreciate the opportunity to moderate today's panel. And we have a group of outstanding researchers and innovators. The speakers have diverse and complementary expertise in areas relevant to thermal effects on the performance and safety of batteries. Each panelist will talk for about 10 to 15 minutes, and the remaining will be discussions and Q&A. Next, I'll provide a brief introduction from each speaker in the order of their presentations, and I'll introduce all of them right now and then pass the sharing screen to them. Our first panelist is Professor Xiaoyang Wang from Mechanical Engineering at Penn State. He's the director of the Electrochemical Engine Center, and he serves on the executive committee of the battery division of the Electrochemical Society. His research expertise is in the areas of thermofluid sciences applied to energy system, transportation, batteries, and fuel cells. Xiaoyang has received numerous recognitions for his contributions, including induction to the National Academy of Inventors. The next speaker is Professor Yi Cui from Stanford University, Department of Material Science and Engineering, the Photon Science Directorate, and the Precourt Institute for Energy. His research areas are in synthesis and self-assembly of nanocrystals and nanowires, transport in nanomaterial, nano interfaces with particular applications to electronic and photonic devices, solar cells, fuel cells, batteries, and more. He was also recognized with a number of awards, including the Sloan Research Fellowship. Our first speaker and presenter is Dr. Ahmad Pesaran, Chief Energy Storage Engineer at NREL, National Renewable Energy Lab. He has a long trajectory of remarkable contributions in research related to transportation, electrical vehicles, including hybrids, automotive batteries, as well as lithium-ion battery safety and battery recycling, which is indeed another key emerging area of research. Ahmad is a fellow of the Society of Automotive Engineers and a strategic member of the US Advanced Battery Consortium. And our fourth presenter and panelist is Dr. Eric Darcy from NASA Engineering and Safety Center. He's the lead in the battery technical discipline with tremendous expertise in battery safety and lithium-ion batteries. Eric is the recipient of the R&D 100 Award and was named the NASA Ambassador Fellow. Next, let me say a few words about the agenda and how we will handle the Q&A. As we said, each panelist will speak for about 10 to 15 minutes, and then we will have the Q&A sections for the remaining about 30 minutes or so. It's advancing on its own. Anyhow, let me continue. To submit your questions as a participant, to submit your question to the panelists, please use the Q&A icon in Zoom. We will not have the chat option, so use the Q&A icon in Zoom. The questions will be visible only to the moderator and the panelists, not to the participants, and we will choose questions from those we receive. We will also indicate the name of the person asking the question, and if you prefer to remain anonymous, please say so. But our preference is to attach a question to a name. I'd like also to notice that this colloquium is being recorded and will be posted on YouTube. We will also post online the questions which we may not have time today to respond lively. So next, I pass the sharing screen to the first presenter, Xiaoyang Wang.
Can you? Oh.
It's at the end of your slides. Yeah.
Oh.
You just need to scroll up.
Now, you still see my two screens, right? Or
Yeah,
just one?
Go to display settings at the top.
Okay. Should I duplicate? How about now?
Yes.
Good. You can hear me too, right?
Yes, we can.
Great. Thank you, Christina, and also thank you again for organizing this curriculum. I think this is touch upon a very important topic. And also, hello, everyone. Thank you so much for being with us. I will highlight just a few basics of the battery thermal management and safety, and then I will, let my colleagues on the panel give you much more depth. Okay, so lithium-ion battery involves basically an anode and a cathode and then an electrolyte in between. Okay, so during charge and discharge, you have lithium ions shuttling between the two electrodes, and this is how the lithium-ion cell works. And a common material for the anode is usually carbon or graphite, whereas the cathode may consist of metal oxide, layered metal oxides, or leaving lithium iron phosphate. So, and both electrodes involve what we call the intercalation reactions, where the lithium ions can be inserted or extracted during charge and discharge. Now, here's a quick review of how a lithium-ion cell is built. So we started out with a solvent preparation by mixing active material powders, whether it's a graphite or metal oxide powders, with binders and solvents, and then we go through the first stage, so-called electrode production. So you do mixing, and here are a couple of pictures showing the mixing and coating, followed by coating, calendaring to get the right porosity of electrode and thickness, and then you cut it, we call slittering. And once the cut electrode are made, and they were transferred to the second stage, which is called the cell assembly. So in the cell assembly, those electrodes will be wound together with separator into a jelly roll for cylindrical cells, or they can be stacked up for prismatic cells. So this is a stacking machine. And once those jelly rolls or stacked electrodes are made, and a picture showing here, and they will be put into a case or a pouch. And after drying and vacuum, you fill up with electrolyte and seal the cell. And then basically you have a lithium-ion cell. And then you go through the last stage of cell formation. So it's a bunch of small current and voltage processes to get the SCI layer formation and stabilized and all that stuff. And so after that, the cell will be ready to use. So this is a very quick review of how lithium-ion cell is manufactured, right? Now, coming back to the first topic of this curriculum. So battery thermal management obviously is tremendously important. And the most important equation, or the fundamental equation governing battery thermal management, is this heat balance between the heat generated from a battery cell balanced by the heat dissipation from the cell, that with a heat transfer coefficient, surface area, and then the cell temperature minus the ambient coolant temperature. Okay. Now, once this balance is maintained, you would have zero temperature rise, and that's a perfect thermal management, right? So let's examine a little bit.
Chao Yang, you are on mute right now.
How about now? Good, okay. All right, so once you, let's examine some of the detail of each of the term in this key equation. So heat generation rate from a battery. Oh, I don't have a control now. Oh, here we go. So heat generation rate can be easily calculated from the power times the inverse of efficiency minus 1. So let's take a look at, example. And for a passenger car, typically peak power is 100 kilowatt. Then immediately for a battery with 90% round trip efficiency, we are talking about 10 kilowatt heat generation from a battery pack. And similarly, for a fuel cell with 50% efficiency, you will be talking about 100 kilowatts. So it's a 1-to-1 ratio between heat generation and power, right? On the other hand, for ICE, internal combustion engine vehicles, with 30% efficiency, and the heat generation is actually tremendous, 230. So in comparison, you could argue that the amount of heat generated from battery pack is pretty small. Second term, temperature difference, delta T, that is driving heat dissipation from the cell. And again, if you look at the three cases, for the battery powertrain, and we are usually talking about 35 degrees Celsius cell temperature dissipating heat into 25 coolant temperature. So you talk about delta T of 10. On the other hand, for fuel cell powertrain, which operate at 80 degrees Celsius, you have 55 temperature difference and 95 for ICE, whereas the coolant for ICE typically runs at 120 degrees Celsius. So the temperature difference is tiny also for battery powertrain. And for those of you who are thermal engineers, and your job really is to design and engineer this H times A, right? So in this case, it boils down to about 1 kilowatt per degree for batteries and 1.8 for fuel cell powertrain and 2.4 for ICE powertrain. So immediately you can learn that, a few things. And number one, heat generation battery actually is tiny, teeny, if you compare with other devices. And battery cooling, which boils down to H times A, shouldn't be a much challenge if you look at those numbers, right? And if we can further increase the delta T for batteries from 10 degree right now to 35 in the future, and assuming the battery would operate stably at 60 degrees Celsius, then the H times A value will be an order of magnitude lower than that for ICE. So it would be, we probably can make the battery thermal management problem go away that way, right? So here again, let's explore a little bit more about this key equation and each of the terms involved. And this gives you a lot of actually basic ideas about how to do thermal management. So in terms of heat flux, expressed in the unit of watt per square centimeter, for the battery cooling, it usually is less than 1. A lot of times it's much less than 1. And that is compared to greater than 10 to 2 for electronics cooling. So we're talking about 2 to 3 orders of magnitude easier job for battery thermal management or for battery cooling. And the heat transfer coefficient is usually related to what we call forced convection or natural convection in the practice of battery management. Whether you use a liquid or air, this all impact the heat transfer coefficient. And there's not much talk right now about radial cooling, but I think in the future, it could be a future area for exploration. We talk a lot about heat transfer area, A, in thermal management for batteries, and through extended fins, aluminum, surfaces, cold plates, and heat sinks, and this is all those techniques are often employed in battery thermal management, and that boils down to A. Now, delta T, that factor has been not so much played in the research and development. I think has been largely overlooked. But one could imagine that if we can engineer or modify battery genes to operate stably at higher temperatures, say at a 60 to 90 degrees Celsius, and to make batteries more like fuel cells, right? PEM fuel cell, polymer electrolyte, membrane fuel cells. And then you have a tremendous delta T, and that will make the task of battery thermal management. Really, really easy. One last note that I want to put down here is about phase changing material, because this is something also has been researched and suggested in the practice of battery thermal management. And now, aside from numerous problems with, PCM and solid liquid phase transformation and the leakage problem and all that, but for phase changing material, I would look at the most important parameter, and that is energy density, because phase changing material essentially is thermal energy storage. It's very much like battery as electric energy storage, right? So we should look at the thermal energy density. And if you take the typical PCM like a wax, it usually has a latent heat about 200 kilojoules per kilogram. And if you convert it into watt hours, so divided by 3.6, a factor of 3.6, that boils down to about 55 watt hour per kg. And now this can be compared to the energy density of lithium-ion battery, which, we talk about 200 to 300 watt hour per kg. So immediately we know those PCM materials has very, very low energy density, probably 5 to 6 times lower than lithium-ion batteries. And you would, always want to think whether or not you want to use something that is low energy density, which means, heavier and bulkier materials to do thermal management. So that's something I want to, mention to the community as well. Now, in terms of the safety, normally we characterize the battery safety using this so-called thermal runaway curve, where you basically show the cell temperature rise and running to the sky over time, and in different temperature ranges, different chemical reactions involved, and typically below 80 to 100 is safe, and then about 100 you have SCI layer decomposition. After that you have anion graphite solvent reaction, which is also exothermic, increase the heat and temperature, and then it leads to electrolyte decomposition. Once about 200 degrees Celsius, you start to see some cathode what we call onset of instability, and that will make the cathode release oxygen, cause combustion. Eventually you have flame, fire, and explosion. I think my colleagues on the panel will get in a lot more in detail into this thermal runaway event. But all those reactions described in this thermal runaway curve actually account for chemical reaction only. So, such as, we often talk about electrolyte flammability and cathode onset of instability. And in this discussion, there's a lot of talk about, NMC versus LP, because, the onset temperature for instability of NMC is around 200 to 250, whereas FP is much higher, probably more than 500 degrees Celsius. But in addition to chemical reactions of, battery materials, we also should realize that the battery is actually a device that is capable of discharge energy. So once you have internal shorting or external shorting, the battery will be able to release all the energy contained in it. And that consequence of electrochemical reaction, okay, in the presence of shorting, can be best quantified by this so-called adiabatic temperature. So adiabatic temperature is basically assuming all the energy released by a battery will be absorbed by the thermal mass of the battery material. So that makes E equal to, okay, I think I need to go really fast, right? So that makes the electric energy equal to MCP delta T, which gives you the maximum temperature rise after all the electric energy is released. If you do a simple manipulation, that is energy density divided by CP. So let's do a very quick example. So solid state batteries, we hear every day in the medium or in research papers, and they claim to have 400 to 500 watt hour per kg energy density and at the same time super safe. But if you calculate the adiabatic temperature rise, it's between 1400 to 1800 degrees Celsius. So obviously everything is gone, even if you have very non-flammable electrolyte, solid electrolyte, right? So we have to be careful when you claim that the solid-state batteries are safe. Even if only 10% of the energy is released, we will see the cell temperature rise between 170 to 200 degrees Celsius, and that's already causing the melting of lithium metal on the anode side. So now you have solid electrolyte, but the liquid anode material, which will cause internal shorting with cathode everywhere. So it's a very messy thing. Once we understood the basic numbers and the basic equation, then we can actually do engineering and thermal management of safety pretty quickly by using with the help of software. So here I just show a quick overview of how we do actually a complete solution for thermal management and safety. So you start with, let's say, a complete CAD drawing of modules consisting of multiple cells, sometimes hundreds of cells, and together with cooling channels. And you can automatically generate mesh and to create thermal fluid simulations and fully coupled with electrochemistry and electrochemical models. And that basically give you a digital battery that you can put in any kind of virtual testing of performance and abuse. So one of the software is available from this company called Gamma Technologies. Also, once we understood the fundamentals, we can actually start to create some simple innovation. One example I show you here is called Safe Energy Dense Battery, or SEB, and that can achieve high safety and high energy density simultaneously, right? And our strategy is very simple. And what we do is we basically design and build a very, very stable batteries using stable materials and very low reactivity interfaces. So the result is, and the battery itself, when it's not used, is highly stable and has a very high safety and low degradation, right? So it's a cool battery, as cool as a cucumber, right? But then right before you drive or use the battery, we can actually use a thermal switch to change it into the high power mode for use, right? So that is, thermal switch can be activated by heating. So we, with that kind of battery, you can actually, with that kind of very stable battery, you can actually achieve more than 4,000 cycles, and that translates to, what originally or initially said million-mile battery. But in our case, this is even million-mile operated at 60 degrees Celsius, right? Under very harsh environment, we could still achieve million-mile batteries. It's very safe, and you can see that the black curve is the internal or the charge transfer resistance or baseline, and all those other colors ones are the SEB batteries, and we see much larger charge transfer resistance. So sometimes highly resistive batteries are very good for safety, and indeed, if you do near penetration. And for SEB batteries, the highest temperature rise is only 100 degrees Celsius versus almost 1,000 degrees Celsius for the baseline. So we could achieve a battery that is energy as dense as NMC graphite, but as safe as LFP graphite. Okay. So very quickly, I'm putting a summary here since I'm running out of time. I think for battery management and safety, we need more fundamental thinking, and from basic numbers and back-on envelope calculations are very useful. In terms of actual design and development, we can rely on simulation-based tools and techniques. I expect abundant technical innovations in the years to come, because I think we now understand very well the fundamental mechanisms of battery management and safety. And one of the innovation I believe we believe that is useful for the future is coming up with a switchable electrochemical interfaces. Right, so when we don't use the battery, we can turn it off. When you need the battery to produce power, you turn it on, that kind of thing, rather than it's always ever-present electrochemical interfaces right now. And I would say, as a final word, and I always find the most difficult job or task is to make our ideas simple, our innovation simple, so we constantly, working towards that goal. So with that, I'm going to stop here, and then stop share and turn over to Yi, right?
Yes, let me jump for a moment. Thank you, Chaoyang. Also, I'd like to remind the presenters to keep the presentations to 10 minutes so we have enough time for Q&A. And I'd like to remind the participants, the audience, to start sending your questions through the Q&A icon on the Zoom screen. Next, Yi Kui, Professor Yi Kui.
Yeah, thank you, Christina, and thank you, Chaoyang, for the very nice introduction already on the thermal, the thinking of temperature, the thermal issue on the batteries. Now let me go down to, I would say, deep inside the batteries, right, and the more small length scale, and down to materials and chemistry, and give you an introduction on the thermal effect. Chaoyang already mentioned about the basic battery cells, so I won't repeat that. But I want to mention is this related to thermal, the temperature issue. During the operation, this electron transport needed, ion diffusion needed into liquid electrolyte. These are the liquid, carbonate, flammable electrolyte. And also, in the solid state is particle, whether it's graphite or is, the lithium metal oxide cathode. Well, this structure and volume transformation going on right there. There will be strain buildup. And also remember the interface between the electrode and the electrolyte, particularly in the negative electrode, the graphite side, this SEI, so-called the solid electrolyte interface. That's the self-decomposition compound of organic electrolyte coating indicated right here on these particles, with this very thin layer of coating in the order of 10 to 30 nanometer range, having the ion coming in and out, and this one will be affected by the temperature quite a bit. So during the lithium-ion batteries operation, if you plot the potential, the voltage right there, for the cathode on the top, the curve, the anode at the bottom right there, if you look at this, well, if you look at the anode, during charging, lithium ion coming in, electrons coming in, you have this plateau, the graphite start to take in a lot of lithium, and make sure you don't go below the graphite potential to go down to lithium plating. If it's 0 watt below that versus lithium metal, you can deposit lithium metal. So I'm going to come back to that and how temperature will affect this process. And right here, this SEI formation below roughly about 1 watt, 1.2 watt also, you start to decompose the electrolyte, forming this solid electrolyte interface. On the cathode side, you are going to charge it up, the potential goes up, you see the plateau. And then once it goes over to a certain voltage, roughly about 4.2, 4.3 watt, you start to worry about the electrolyte oxidation. Anode side is the reduction, cathode side is the oxidation right there. The temperature will accelerate oxidation on the cathode side. So that's something you need to take care of, think about once the thermal issue really comes in. So then how does the temperature affect its chemistry? We know in the cold weather, when the temperature is very low, electrolyte resistance goes up because it's more viscous and you have low power output right there. And the lower temperature, you want to push lithium going to graphite during charging. However, this push-in process becomes slower, and then you can potentially have lithium plating happen easier. Then this can cause dendrite formation and potential battery shorting. And also remember this is electrolyte freezing. If you go to the really low temperature, this can cause a physical damage. And the high temperature is a different effect. Of course, you have high ionic conductivity, but something you have to worry about is the side chemical reaction becomes more. On the anode side, SEI, on the cathode side, more oxidation. So you need to really pay attention to that. That can potentially shorten the battery life. Then if we look into further, Chaoyang give you an introduction about, well, when I operate my batteries right there, I will have heat generation inside the batteries, right? And particularly under fast charging, increase the charging speed, you're going to have more heat generation for given time, and you will build out a temperature gradient even more. Having this temperature effect right there, this left-hand side is really plotting to you, the fast charging. Once you go to the XFC, extremely fast charging condition, you are really using the power in the order of close to 300 kilowatt of the power. Under this condition, there's many effects. The temperature can really affect the processes under the fast charging condition. The first one will be you have this lithium transport profile. During charging, the anode will taking in lithium, the cathode will, the lithium coming out, ion coming out in the cathode side. So you build up this concentration gradient. Then the thickness of the electrode will affect this gradient a lot. You want to go down to thinner electrode usually to avoid these large gradient profile right there. So this electrolyte conductivity, transference number, electrode thickness, and tortuosity will affect these lithium transport. So certainly temperature will also affect that. Higher temperature will help reducing this gradient. And then the charge transfer across the interface is very important as well. So lithium and the electrolyte solvated by these solvent molecule, it needs to get desolvated. Desolvation will take place across the SEI interface and then transport into the graphite right there. So all these processes can be affected by the temperature as well. The next thing is the temperature inhomogeneity will build up. I'm plotting, showing a cylinder cell right here, but it will be similar. Pouch cell will have this effect right there. In the middle, in the center of the battery will get hotter. Outside will be, when you get to the outer surface, approaching to room temperature, you are going to have temperature gradient inside the battery cells. This gradient will cause the problem of, certainly higher temperature will give you faster kinetic, higher current, but higher current will also drive the heat generation even more. So this can become a positive feedback loop. And then the higher temperature part will get cycle, charging and discharging more. The current density is higher compared to the lower temperature part. This can potentially create issues. Let me give you one example. So what issue can create is with this temperature inhomogeneity. And this experiment we conducted, really using the local laser to heat up a current collector on the anode side. So you have this local hot spot. And we could use the graphene on the top surface using the Raman ship to indicate what's the temperature right there. It is a linear relationship between the power and the these Raman ship right there. So under this condition, if you look into this, the top row is the SEM of during lithium plating, and the location, the spot, you have higher temperature. When you have the laser heating on the backside, you can see there's a lot more lithium metal deposition taking place right there locally. And through a careful study and thermal simulation, we found out, this higher temperature local hotspot increase the so-called extreme current density, increase the kinetics of deposition of lithium a lot more. So you can locally amplify by using temperature of this deposition, and that can cause potential shorting of the batteries right there. So these, we want to point it out, this temperature inhomogeneity can cause actually quite a complex effect right there in the lithium metal battery charging. I also want to emphasize the temperature effect affect the thermodynamics of the battery electrode, particularly the potential. The potential relationship, also the voltage, is related to delta G of the reaction, right? If you look at the delta G, how that translates into the voltage is using this Nernst equation right there. That's the origin of the voltage of the electrochemical cells. So then the voltage temperature coefficient is indeed related to the delta S, the entropy of the system. And the electrochemical system, and this delta S turned out to be actually quite big because of this solvation energy right there, solvation entropy, as well as the lithium ion or other ions, if you look at other systems. And the solid state can provide the mobile ion quite a bit of entropy contribution as well. In the early days, back in 2014, in collaboration with Gang Chen, we have a joint postdoc, working together right there, and already showing using the high entropy of the electrochemical system, we can utilize that to harvest the waste heat, convert it back into the electricity and store and use. That was the early indication of a very larger entropy or larger temperature coefficient right there. Now let me share with you under the lithium-ion system, and what's the implication right there. And this lithium battery electrode, we actually can design and measure the temperature coefficient of the voltage using this H cell, right? H shape of cell. The same electrode, these flasks, they're sitting into a different temperature. We measured its voltage, open circuit voltage can determine the temperature coefficient. That's when you change the temperature, you measure OCV at different temperature. And this is for lithium metal. And then we can measure the graphite as well. And you plot this. This is the voltage change versus temperature. This indeed is giving us this linear temperature coefficient in the order about 1 millivolt per Kelvin, also per degree Celsius. So this is actually very high temperature coefficient right there. What does it mean right there? Once you increase the temperature, the voltage goes up, right? Imagine you have a battery cell electrode, and there's a temperature inhomogeneity in there. This is for graphite. In the middle right here is higher temperature. Its potential lithium plating will go up with temperature. Once it go up to the potential, it's even higher than the room temperature region of the graphite intercalation potential. You indeed will have lithium plating already happening in the hot temperature. Even though in the full cell, you're thinking about your graphite has not go down to the voltage to plate it yet for the room temperature, but for the local higher temperature spot, you already exist the lithium plating potential, so the plating will happen. What I want to say is if you have a battery, the inside is hot, the outside is cold, particularly under fast charging condition, it's entirely possible inside will plate lithium metal, even though the potential, if you think in the room temperature, doesn't reach the plating potential, but for the hot temperature, you already do. So that's actually very dangerous. So let me go one step further in terms of the materials and chemistry. So if you have a shorting happening, and then this shorting can be induced by many reasons. I believe later our speakers right there will tell you more exciting, study on this. And Chaoyang also mentioned, once your temperature goes up, because all these phenomena happening, SCI, decomposition, reaction, chemical reactions start to happen roughly about 200 degrees Celsius also. For the MMC cathode, you can go into the regime of catching fire. So we look at the rate of heat generation through this temperature at about 150 degrees Celsius also. You have the SCI decomposition at, a separator melting. This is happening, building out the temperature, and then trigger the thermal runaway. Temperature goes up very, very fast. So I won't go into the detail of that. So to mitigate that, let me go down to the chemistry level. Is how do you do that? First, what idea I want to point out is it's already in use. People use fire retardant, adding in the additive into the organic electrolyte. And we also, recently, invented an idea and say we need to encapsulate this fire retardant into a polymer. The reason is the more fire retardant you add in, you are going to increase the viscosity of the electrolyte. So lithium-ion conductivity and the electrolyte becomes smaller, harder to battery to operate. So instead, we encapsulate this green color of additive of this fire retardant into polymer. So until you heat to a certain temperature, the polymer melt and release the fire retardant, knowing the danger is coming, release it, and then quench the fire. And we also think about the idea, shorting is an important trigger of the battery safety problem. Can we do something about this? In the industry is already used is the ceramic coating onto the separator to enhance its stability against the shorting. A few years ago, we also come on an idea is inside the separator, you have cathode and anode inside the separator having a lithium metal detection, half short detection. If the shorting happened already halfway, you detect it, make sure you don't do the battery charging anymore. So to avoid the shorting continue to grow to fully short the batteries. So we also consider to add in something like thermal switch onto the electrode coating. If the temperature goes up, this is in collaboration with John Bao at Stanford right here. Temperature goes up, this coating layer going from a conducting, electrical conducting, metallic conduction become a pure insulator. This 8 orders of magnitude resistance change and shut down the electrical conducting pathway so you cannot release the electricity right there, so avoid the fast heat up of the batteries. So I believe that more innovations are needed to enhance these thinking of thermal trigger, the battery safety concern. So in summary, so I was telling you a number of effects right there, the temperature can do to the batteries. I will not repeat this whole list, and I will wait until we go into the panel to have more discussion with you. Let me stop right here and stop sharing. So next, I'll let Ahmad to come up to tell you what I want to share with you.
Okay, can you hear me and see me? Thank you, Yi, and I appreciate Christina for the introduction. Thanks for Dr. Chen and MIT for organizing this. Xiao Yang and Yi provided very good introduction to what's going on with the batteries and science of behind the temperature. So I'm going to talk about the practical aspects of thermal management of BBs. And for some reason, Zoom has decided to give me this background. An EV pack consists of many modules. As Xiao Yang shows you, you have a stack of anode and cathodes that you make a cell out of them. And of course, you put all these cells into a module, and then a module into a pack. And these are LG Chem cells into GM Volt, which is 16 kilowatt. And actually, I show you the picture of these things that is maybe about 5 or 6 years old. And the technology has improved a lot, and you can have in the same volume almost 100 kilowatt hour of battery in there. You can have many different sizes, cylindrical shapes, cylindrical, pouch, or prismatic into the battery pack. So So these series of parallel series and parallel integration of these cells give you the voltage and power energy required, but it needs to meet life and cost targets. So we need to have some battery management system from both mechanical, electrical, and thermal perspective for robust packaging, kind of crushworthiness, vibration, electrical balancing to give you performance and life that you want. And also, of course, other attribute would be manufacturing, recyclability, and maintenance and repair, so that it'd be easy to cost and maintain these things. So there are many things going on into the battery pack. Yeah. So as I mentioned, lithium-ion battery is becoming highly important aspects of electric vehicles because of their high performance and cost being decreasing. As Yi and Xiaoyang mentioned, kind of high temperature degrades batteries. And what kind of degradation we have, you can see here on the left side is the capacity of the battery, which is capacity means equal to energy battery, decreases. A battery that's at 25 degrees C can go more than 15 years. If you put it at 45 degrees C, you can see only have about 5.5 years capacity. So it becomes challenging. And also not only the capacity, but also power capability. The relative resistance of the battery increases and it dies as far as the number of cycles increases. So the power goes down, and power energy relates to range, and power relates to acceleration. So this is a kind of chart here I show you that kind of tells you where the desired operating temperature for batteries is. I mean, Xiaoyang said that kind of the thermal management of batteries is easy because of those. We need to be at low. The heat transfer rates are small. The challenge with compared to the engine is that the engine can run at 400, 500, 600 degrees C and doesn't degrade at all. Actually likes it. But batteries don't like that. Kind of lithium-ion batteries like to operate in this temperature of 15 to 35, and you know that outside is not harsh. And actually, when you said that you have a winter sluggishness and kind of lithium plating, and also degradation happens at high temperatures. So we need to make it happen in this range because it both impact the range and the performance of the vehicle. So as an example of kind of here on the right side, kind of if a battery that doesn't know cooling in Arizona kind of goes down and kind of this 80% limit that we have, you can lose the battery in 5.5 years. If you add air cooling, you can extend like to 6.5 years. If it's even better cooling, liquid cooling, you can extend it almost 10 years. And that's what OEMs or car companies are faced with to do these things at cost effectively. And this is actually a desired attribute of thermal management. It's maybe thermal heat transfer easy, but then you have to keep all the cell desired temperature, minimize cell-to-cell temperature variation in the pack, minimize cell internal temperature in emergency. And we mentioned that the importance of that in homogeneity in the cell, we need to keep it away from happening. Prevent temperature from going above acceptable limits, and also safety limits. And both Ye and Xiaoyang show that what happens if doesn't we do that. So also we need one thing that's very important also is kind of amount of energy that we want to use for parasitic powers for maintaining the operation of the thermal system. You cannot have a big refrigerator run on your back car to keep your batteries cool. You need to have minimum amount of energy used. Of course, low weight and low cost is important. So that's become very challenging. I mean, those small heat transfer suddenly becomes very important. That's on the left side. You have right side. You have a table of the United States Advanced Battery Consortium that kind of sets all these targets about what we want to do with different type of electric vehicles. So let's get into more aspects of what tools we have to design a better thermal management system. Kind of Xiaoyang mentioned a little bit of them, but you need to have characterization tool, experimental tool to measure how much heat you have from a battery. Actually, that's the most important parameter that comes. I mean, at different drive cycles and testing, the kind of amount of heat that comes from batteries is much different. Thermal imaging provide a picture of what's going on with the battery and the homogeneity of the cell inside. You need to know thermal conductivity. It's a heat transfer problem. You need to have a heat transfer characterization set up, and then verify your thermal management system through the loops. We have tools, kind of first order lump capacitance model, examples showed by Chao-Yang. You have 1D, 2D thermal models, fluid dynamics models with them, and then we used to use 1D integration models that all these provide some good information. The chart I showed you in Arizona was done in 1D integrated thermal fluid model. But then we've learned more and become sophisticated. We added electrochemical, now we're adding mechanical crush into these things. And we have computer aided these software tools that Chao-Yang mentioned. But the basic heat transfer of the thermal management is kind of a heat transfer, kind of what's happening, temperature rise in the battery depends on how heat generation, and then the heat cooling rate, or heat, if you want to do heating the battery, the heating rate. The heat generation is reactions, chemical reactions, material phase changes, mixing, and joule heating is the most important. At higher currents, joule heating is that becomes the dominant factor. So the methods of heat rejection, it could be direct air, direct liquid cooling, indirect liquid, play with plates and channels and kind of pins, and and even phase change material. But this is kind of, I show you in the bottom, kind of example of how you can put the battery pack with the rest of the heat exchangers and the air conditioning system that in your system to cool the battery. So it becomes a little bit more complicated as soon as we start building up, and we need to minimize that. So as I mentioned, heat generation is very important. This is an example of kind of how the heat rate changes. So we have at NREL, we have used this isothermal battery calorimeter that kind of measure heat generation as a function of RMS, drive cycles, and you can see each battery is different temperatures, different. We have heat transfer in modules, and you can see here, just going through this with air cooling, there is a temperature non-uniformity about 5 or 8 degrees C within one cell. So we need to make sure that we have a cell that keep it down. Thermal imaging can provide very potential for hotspots that we can see here. Kind of this was the original design of a nickel metal hydride battery in Toyota Prius generation 2, but then they went and did this was hotspots here. Then they went modified it, and when we did thermal imaging, was completely uniform engineering aspects. So these are today's kind of lithium-ion batteries are pretty good. This is where we are right now with lithium-ion batteries. From outside, it looks everything uniform. The tabs can be very hot. I mentioned about 3D modeling of electrochemical-Thermal models that we have, and Chao-Yang mentioned some of it. But let's say how these 3D models can help you. Of course, kind of you design this, say, okay, we'll have this kind of design, kind of the two tabs on the same side, and you work on the working potential, what is the electrochemical production, current production, distribution of current, distribution of the state of charge in the battery, and then what's the temperature distribution. So you know that, and then you say, okay, what if I design, my design changes? So we put the thermal, the two tabs on two different sides. And when you do that, you can see the temperature distribution becomes much easier because current distribution is less and homogeneity becomes much more. And actually, this is Gen 1. That's what actually GM, I think, believed it. Gen 1 cell designed from Chevy Bolt, and now Gen 2 design from Chevy Bolt that's in the Chevy Bolt today. So it's about almost 60 to 100 amp hour cells that has two tabs on both sides. And that's what the reason they went for it. So, and then computer-aided engineering tools can even do from fluid thermal, fluid thermal heat transfer, and all the way kind of, this is a simulation of this Tesla batteries that have liquid cooling around it, of all these 1860 cells. And this is the Bolt liquid cooling, and has thermal cooling plates between them. But you can imagine many different things that is happening. So I'd like to summarize by saying that thermal management is needed. It could be simple at the beginning, but it kind of quickly becomes important because you optimize weight and cost and performance. You have to use the proper tools to design thermal management systems. And of course, currently the indirect liquid cooling with the fins and plates is the biggest standard, people using it, and computer design tools using that. But as batteries get higher energy dense, the charge rate faster, heat rejection become much more challenging. So innovation needed. So I'll be happy to answer any questions later on. So let me share this, stop sharing, and pass it on to Eric.
Okay. All right, so let's see. There we go. So you guys able to see my screen? All right, thank you, Ahmad. And so I'll speed up here and basically tell you some of the applications that we've been able to achieve and get into particularly a high power where the thermal management is critically important. And we've been trying to achieve safe batteries that also are high performing. Particularly the goal is to get to 160 watt-hours per kilogram in specific energy. We're looking at this for electric airplane applications and other robotic applications and anything that needs to discharge at a high rate. By high rate, I mean 3C 20-minute discharges. Been able to do this with a really good group of diverse folks. I used Dr. Ralph White at South Carolina for the modeling aspects, did some real assembly work with a small company in Alabama, and then some new technology that's making it all possible with oscillating heat pipe at Thermovant Technologies. So I'll briefly just get into the challenges and the solutions and highlights of our testing or verification of achieving passive propagation resistance so that we're tolerant to single cell thermal runaway. And that's what we mean by achieving safety. We want to be resistant to a single cell going into thermal runaway because that's the one failure mode that we can't put a fuse on or can't put a positive control on. And even though they're rare, occurring in about a 1 in a million probability from manufacturers that have their processes under control, every once in a while, even a reputable manufacturer will make a bad lot. So we need to be prepared for that. Plus, we also have a requirement that no flames exit the battery enclosure in our spacecraft. And then when we get to high voltage, we also have to have dead facing of our connectors for electrocution hazard control. And then we also have a corona discharge hazard when we get to low pressures at high altitude. Yeah. So our baseline is to use commercial cells that are readily available for users that achieve the requirements here. We went from our database, our previous experience with high energy packs is to go with an interstitial aluminum material that provides a good heat conduction and also provides support for the cans when they misbehave and go into sidewall rupturing as opposed to venting out the top or the bottom. When you have a sidewall rupture like I'm showing here, you can get some defeat pretty much all the features that you've placed in the battery to prevent propagation. And so you need to handle that failure mode first and protect it. We found when you try to push this type of approach with a very thin interstitial aluminum heat sink, that amounts about a 20% mass fraction. You can't move the heat out very fast, and you get large temperature gradients between the inner cells of this hexagonal pack to the outer cells of that pack. And so it's just not, it won't work and to be able to for a 3C or a high rate discharge. We've got to go to a different solution. So then we start looking, okay, well, how do we get the heat out of these cells? And are there limits to what we can achieve with just an axial contact down the length of the cell can? So here in a big aluminum block, we put the cell in and we provide very good heat sinking. And we found out that high energy cells the ones that are achieving 270 watt hours per kilogram, and commercially it's 50. If you do too good of a job of cooling them, their capacity it really drops off very quickly. In fact, the MJ1 cell from LG in this example here only produces about 2.2 amp hours at the 3C discharge rate of 9.6 amps if you keep it at 25 degrees. So these high energy cells have got to run hot. By running hot, they got to run over 50 degrees in order to deliver a nameplate capacity. And that I mean somewhere around 3.2 amp hours. So this pointed us to, we need to go to higher power cells, give up some capacity. And here's a comparison of a high energy, high power cell, the Samsung 30Q, versus a high energy cell, the Panasonic GA. Both at the same 3C discharge rate, around 9.6 amps. And you can see that the Samsung cells were running at a higher running voltage, provides a more total energy. This was better suited. We give up a little bit of nameplate capacity at the beginning, but we have a better operating window at the 3C discharge rate. We don't have to run it right between 50 and 70 degrees Celsius. So we started looking at a spine heatsink approach with every cell is attached by a bond, an epoxy bond, to a spine heatsink. We looked at solid aluminum, and then the advanced technology I'll tell you about is the oscillating heat pipe. So we put 16 cells in this type of an assembly. And here we ended up with a 60-degree contact angle. And I can tell you that we studied that, and it didn't really matter how big the contact angle was. And the rest of the spaces were filled with ceramic putty, the high temperature ceramic putty material. We also put rings around the stainless steel rings around the spin groove of the cells, which our previous studies have shown that that's the most vulnerable area of the cell for sidewall rupturing. You put all those 16 cell assemblies, 6 of them together in this, what we call a battery deck with 96 cells, and we're able to achieve 160 watt hours per kilogram with this, that Samsung 30Q cell on that. If you don't have a high rate application, you can get 192 watt hours per kilogram by using a high energy cell and running it at lower rates. But we're specifically looking at high rates here. And so we put 2 of these decks into a box like this with some flame arresting features and a commercially vent assembly with a gas permeable waterproof membrane from the folks at Gore, which are targeting this for electric vehicles. And then we studied the spine. What kind of thermal conductivity would we need from the spine? What type of epoxies did we need to use? And how important was the heat generation aspect from the cell into that? And we found out that the thermal conductivity of the spine the thermal conductivity of the epoxy bond, we didn't have to use any fancy epoxies. It didn't really matter that much. And the contact area, that contact angle, whether we use 120, 80, 90, even down to 30 degrees of contact angle from the cell to the spine didn't matter as much as the thermal conductivity of the spine, the heat sink spine. That's the big factor. And also anything we can do to reduce the cell heat generation. Going from the high energy cell to the high power cell really mattered quite a bit. And so that told us that we would never get there with a solid aluminum at the higher 20-minute discharge. We needed to go to something that was much more conductive. The oscillating heat pipes is with these micro channels and loaded up with ammonia from a company that has the IP for this. It's a Thermovant Technologies, their website over here. I encourage you to go to that and learn more about their technology. But it greatly reduces the thermal gradients between the cells. Here you have a side-by-side analysis comparison. If you went to a solid aluminum spine, we'd have temperature gradients between the hottest and the coldest cell of 19 degrees. While the oscillating heat pipe with the ammonia bubbling and condensing that occurs from the middle to the ends, greatly reduces that thermal gradient from the hottest to the coldest cell to 2 degrees Celsius. That's what the modeling predicts. The modeling also predicts that they are equally good for protecting against a single cell thermal runaway. The thermal runaway cell reaches up to 600+ degrees, but the adjacent cells are protected. They are kept below 100 degrees Celsius, and that's the name of the game here. And this is with 2 millimeter spacing and our ceramic putty as the interstitial material. Most of the heat is shunted into the spine or the oscillating heat sink spine. Here's what assembly looks like. And these are the 16 cell assemblies. Here's that ceramic putty I was telling you about, showing some of the wiring for the thermistors. So we put these two decks together into one box. They're in series for a 100-volt battery pack, 2 kWh. And in order to trigger thermal runaway, we use the NASA NREL internal short circuit device, which is embedded inside the cells and has a wax layer that melts at 57 degrees and produces a hard short due to the winding tension that's in the jelly roll. This is what we think is the most relevant or best way to represent a field failure of a hard internal short. It allows us to only have to heat the cell to over 57 degrees to produce a hard short that produces a thermal runaway response. Makes it a lot easier to trigger thermal runaway with a lot less biasing of the adjacent cells. So we implanted these cells or built these decks with these trigger cells in these locations here that I'm showing. So we had a mixture of corner cells, interior cells, and also some edge cells, as I'm showing over here. So we had 6 total trigger cells in our test campaign. We've connected all the cells in a S before P configuration. That means we put the cells in series and 12 cells in series, and then connected strings of those 12 cells in series, so that 8 in parallel. So we had 2 decks, and the 2 decks were then in series. We put an arming plug with a fuse embedded for our dead facing requirements, so we could take out this arming plug when we're doing the assembly work and put the arming plug at the very end when we want to energize the pack. This is photos of showing you what the pack looks like. As you can see here, we had some mica covers on every tops of every cell, and that's so that when the trigger cell goes into thermal runaway, it blows through its mica cover, and mica is a very high temperature material. The adjacent cells then are protected from the ejecta. Oh, and what I'm showing over here, and here's our little heater, our homemade heater to heat up the trigger cell in order to drive the thermal runaway response without it heating all the other cells. Here's what the full pack looks like during the assembly. As you can see, our 2 decks and then our wiring our flexible bus bars that go to the arming plug, and then our power connectors over here. And then I've got a video that shows a thermal runaway test of a single cell. And that meets our requirements, a very boring test where only smoke comes out and no flames exiting the battery enclosure. The trigger cell gets very hot as expected, but the adjacent cells here stayed below 100 degrees Celsius and were very well protected. This is what the pack looked like after all 6 runs were done. We were able to charge and discharge this pack in between runs in order to clean up the pack and refresh the flame arresting features to clean them up to make it valid for the next test. So the summary, when we went and took apart this pack, we inspected the trigger cells. We didn't see any sidewall rupturing on any of the 6 cells. And we did have some bottom rupturing in the M36 cell. But we were able to handle that. As long as it doesn't go through the sidewalls, we're good. So we thought the putty did a really good job of protecting and providing support to the can wall of these cells, especially these high energy cells. The can walls are getting thinner and thinner, and so they need to be protected. So overall, the adjacent cells were well protected. So we did 6 of them, 2 corner cells, 2 edge cells, 2 interior cells. Maximum temperatures were just above 100 degrees on some, but we were able to cycle the adjacent cells afterwards or cycle the battery. So it showed that we had good margins against that. So we did get one run where we got some circulating currents afterwards. We have a way of protecting against that to improve, but overall that didn't damage the adjacent cells. And overall, our S series before parallel topology provided us with some really good robustness, so that we were able to cycle the cells before and after, or cycle the battery before and after. If we had used a P before S topology, we would have had to use fuse isolation on every cell, and that would have added impedance to the pack and reduced the power of the pack. So the takeaway message is that it is possible to build these battery packs that achieve high energy and high power and be safe. By high performance, I mean 160 watt-hours per kilogram. We need to use high power cells. That's a big lesson learned from that. We need to protect the spin groove of the adjacent cell, of all the cells, and that's the most vulnerable area. And the oscillating heat pipe technology is working really well for safety, and we're about to test it for performance. We haven't had a chance to share those results with you yet, but it's looking really good on that. So we've did some subscale testing prior to all this that I wasn't able to share with you, but that all supported that all the little features that we put in here, such as the blast plate in between these decks, does perform and provide a light pack. So with that, I'll turn it over and stop sharing and go for your panel questions.
So thank you to all our speakers for your insightful presentation and for sharing your knowledge with this large audience that is attending today's seminar and panel. A reminder that the way for the audience to interact with the panelists is through the Q&A icon in Zoom. We have already received a large number of questions, and let me pose the first one to any of the panelists. Most of you referred to lithium-ion batteries, which are certainly the most commonly used in electrical vehicles and portable electronics, with different chemistry from the electrodes. We expect that lithium-ion batteries will continue to be used for many years in the future, with, as you indicated, many improvements yet to come. The first question is regarding solid-state batteries. Could you share with us the stage of development, when we could expect to have them in mass production for consumer products? And as pertinent to this colloquium, what are the thermal challenges we expect that solid-state batteries will have? Yeah, Professor Wang mentioned a little bit of the density issues. Maybe you can address some of these issues.
Sure, I'm going to make it quick. I think the commercial mass production solid-state battery probably will be after 2030. And there's lots of challenges that need to be overcome scientifically and engineering-wise. Now, one thing that we do know in terms of its impact on thermal management is basically the fact that almost all solid-state battery would have to operate at an elevated temperature, something about 60 degrees Celsius. So I think we have to recalibrate how we do thermal management.
Excellent. The next question from Nicholas Jankowski goes to Dr. Ahmad Pesaran and says the following: for current SOA vehicle battery packs, is heat generation volumetrically uniform? On what scale are the cell thermal time constants relative to realistic vehicle heating transients? And are we near the point where we can't just apply external cooling schemes and need to look at integrating thermal design into the cell itself?
Thank you for that question. I think the heat generation can be non-uniform in the cell at high rates. As you saw, that kind of depending on the geometry, if the terminals are different size, the current distribution could be different. So heat generation depends on the current distribution inside the cell. So as a result, you have one of the things that transient when you, because of the thermal mass of the battery that we have, you have a large battery pack. Transient kind of when you accelerate quickly in a car, that's what I'm understanding from your question is, then the high current goes through it, but it goes through a big pack. So the spike in temperature is not as significant as the spike in the power from the battery, from the vehicle. So, but it takes a while to come. So thanks God that you don't accelerate for 2 hours. But for fast charging, that can happen because you're fast charging at 6 or 60 rate, something that for 10 minutes. So that's a different thermal management required for those kind of things. Some people talk about the thermal management for on operation of the vehicle and some during the fast charging. So the other question was that can the heat rejection would be in a cell itself? Maybe for solid state batteries that we need to do that. But I think for lithium-ion batteries, it's going to be very challenging to do that. And I agree with Xiaoyang that kind of, he was not kind of late 2020s is the one that solid state battery may come to market. We're going to have lots of advanced lithium-ion batteries for a long time to come.
Thank you. We have time for only one additional question from the audience. Let me choose the question from Yang Yen Zhu, and says the following. It seems that thermal management is mainly from outside the battery. Could internal thermal management without compromising energy density too much be worth pursuing in combination with cooling the exterior?
I think this is a great question. I think people have not been able to explore the internal cooling yet. So this is from Yang Ying. I think I know Yang Ying UCSB. These require very innovative solution. Certainly on top of my head, I couldn't think of anything yet. But if something that could be done, enhance internal cooling, reduce the center of the battery, the temperature gradient from the outside, right? So far you have this multi-layer of electrode separator, multi-layer stack up. Separator is not a good heat conductor right there. So somehow you can enhance that. I think that could be fantastic. Yeah, maybe something could be done in a very innovative way.
My response that is possible, probably something for Eric's application that has cost is not that important. The mission is so important, so you can spend a lot of money. But for vehicle applications, the cost is very sensitive. So anything you do with inside the battery has to consideration the cost.
Thank you. Let me pose a final question from the long list that we received that goes to Eric Darcy and comes from Cody Iacobucci. And it says the following: how far are we from electrified urban air mobility and hybrid medium to long range flight? It is hard to overcome the fact that a good portion of batteries is dead mass in flight once used, and that energy densities are still low compared to fuels. But it is essential that we solve it to reduce aviation emissions.
Well, it's a good question. It's looking at my crystal ball. I would say for short-term duration flights, like 1 hour flights, eVTOL aircraft, the electric vertical takeoff and landing flying vehicles, I think is the question. I think that could be within 5 years is possible. It's going to require a lot of innovation. But I think that's doable. As far as going to longer range for hybrid systems would have to work. This is where fuel cells and other type of propulsion systems, chemical propulsion, a hybrid would work such that the batteries would only be there for the takeoff and the landing, where noise is much more of an issue.
Thank you. We're very grateful to our distinguished speakers for your excellent educational presentations and for the enlightening, informative responses, many of which will come and we will be answering them online. Let's see. And also thank you to the audience for your participation and your insightful questions. We received many more than what we could possibly cover. And as we said earlier, we will post the questions online along with a recording of this colloquium on YouTube. So I want to say a few words about the next colloquium, which will cover the topic of extracting water from air with an exceptional panel of international experts. It will be on July 8th, which is 3 weeks from today instead of the typical 2 weeks in between Colloquia, because 2 weeks from today is July 1st and it's a holiday in the US. And 2 weeks after, on July 22nd, the topic will be high thermal conductivity materials. Same time, same Zoom link, and all of you are invited to participate. A few final words. I want also to mention that building on today's topic on batteries, we're planning a follow-up colloquium in August on thermal management of electrical vehicles at the system level to discuss some of the emerging trends and the new engineering challenges. Now, the organizers are very interested in your feedback for future events, your feedback on speakers, on topics, on format, and also what would make this colloquia an even better experience. You can also sign up to receive notices of future events by email. And a reminder that you can find videos and Q&A sections from past colloquia on the website and on YouTube. After this event concludes, just in a few minutes, we will keep Zoom open for about 5 more minutes. So you can type in your comments and suggestions. A final word from my side, it has been a privilege to moderate this panel with distinguished speakers, great information and education about the state of the art in these important topics, and with participants coming from every corner of the world. We have over 500 participants today. Thank you all for your participation.
Thank you.